In the previous video, we talked about chaining, which is one way of handling collisions. In this video, we are going to talk about open addressing. Open addressing is another way of handling collisions. The idea of open addressing is to use single array only, not to form any chains of any other data structure. Your all items, they go into this single array. So one basic requirement for open addressing, your number of slots in the hash table or this array size, it should be greater than or equal to number of keys to be inserted. So if you want to insert 100 keys, your hash table size should be at least 100 because you are going to insert everything into this same hash table, right? So this is one basic requirement of open addressing. What is the advantage of open addressing over chaining? It's cache friendly because you have everything in the same array, so it's more likely to have fewer cache misses. Let's see how does this work. One more thing before we talk about actual example, there are multiple ways of implementing open addressing. One way is linear probing, other is quadratic probing, and one more way is double hashing. In this example, I am going to consider linear probing. Linear probing to demonstrate the example. Let's see what all that means, what is open addressing, what is linear probing. So we are going to use the same hash function. Hash of key is key &7. Our hash table has value 7. Indexes are from 0 to 6. So this function is going to generate indexes from 0 to 6 and we'll put those values at those indexes. And if there's a collision happens, we'll use linear probing. Let's see how does linear probing work. So we'll get the hash value of 50. We got the value as 1. We went to this index 1 and inserted 50 here. Now we get the hash value of 51. We got the value as 2. We go to index 2 and insert 51 here. 49. We get the hash value from here as 0. Right? So I'm just applying this function here. 49 modulo 7 is 0. Right? 50 modulo 7 is 1. 51 modulo 7 is 2. So 49 modulo 7 is 0. So I'll go here and insert 49. 16. 16 modulo 7 is 2. So I'll go to index 2 and now I see a collision. I see a value which is mapping to the same slot which is already occupied. What do we do? So linear probing says that we linearly search for the next empty slot. So we linearly search, we come here and we find this as the next empty slot, right? So linear probing means linearly search for next empty slot. For next empty slot when there is a collision. Let's now talk about 56. 56 maps to value 0. This is occupied. So we linearly search for the empty slot. We come at 50, we come at 51, we come at 16. Everything is occupied. This is where we find a free slot. So we insert 56 here. Let's now talk about 15. 15 mod 7 is 1. We go here, we see that this slot is already occupied. So what do? Please pause this video and try to place 15 here. We search 50 is occupied, this is occupied, this is occupied, this is occupied. We insert 15 here. 19. What is the value of this function for 19? 5. The slot is already occupied. So we linearly search for the next slot and we insert 19 here. One interesting thing for linear search, if you are mapping to last slot and last slot is occupied, you search in a circular manner. You search, you increment mainly your index using modular arithmetic, right? So I'll just take another example to explain this thing. Let us do one more example to understand linear probing and open addressing better. 48 modulo 7, 6, right? So we'll go to this 6 slot and put 48. 42 modulo 7, 0. So we'll put 42 here. 50 modulo 7, 1. So we'll put 50 here. 55 modulo 7 is 6. And this slot is already occupied. So what do? We linearly search for the available slot and we linearly search in circular manner. So this is the purpose of this example. So I'll begin from this slot, I'll go in a circular way, I'll search here, and this is where I'll insert 55. 53, value is 4. 53 mod 7 is 4. So where will I insert 53? At 4. So this is another example to understand open addressing with linear probing. Let us now talk about this problem of deletion when you are using open addressing. Before we talk about the problem, we need to understand the search operation. So let's understand search with these insert and then this search. We are going to use the same hash function here. So we first insert 50. We go to this hash function, find the value 1, we go to the slot 1 and insert 50 here. 51, hash value is 2, we go to the slot and insert 51. 15, hash value is 1, we see a collision, so we linearly probe, we find an empty slot and we insert 15 here. Now I'm talking about search operation, how to implement the search operation. So what do we do when we search a key? We find the hash function again. Our hash function gives us the value 1. We go to the slot 1. We do not find 15. Can you guess what do? You search, you went to the slot and you found that this slot had something else. So what will you do? You will again linearly search. And when will you stop your search? When you encounter 15, you found 15, or you encounter an empty slot, right? So you start from here 50, you go to the next slot, this is not 15, you go to the next slot, you found 15. So you say, okay, I found 15, it's there, I stop my search and return true. Now suppose I have one more search. I have a search for 64. So what will happen when you search for 64? You will begin from here because your hash function is 1 for 64. You will say it's not 64. You will go here, linearly search. You will go here, you will linearly search, right? And it's also not 64. So you will end up with an empty slot. So you will stop your search when you find the value or you find an empty slot. There is one more case, what if your whole table is full? Then you would not find an empty slot. So when will you stop your search? When you traverse in a circular way and come back to the same slot. If that happens, then you say that this key is not present. Suppose this whole table is filled, all the values are filled, and I am searching for 64. So I'll begin from this slot, I'll come here, come here, come here, come here, come here. Since I'm assuming this to be filled, then I'll come here and I'll come back to 50. And then I'll say, okay, I've traversed through the whole hash table. The 64 is not present, so I'll stop there. So when your hash table is full, then you will search through the whole hash table. If your hash table has key that you are searching, then you will definitely find the key and stop there. If your key is not present and hash table is not full, then you will stop when you find an empty slot. So when you were searching for 64, you started from here, came here, and you found an empty slot. And then you said that 64 is not present in the hash table. So let's talk about that. Let's write down the search function. That's how search works. We compute hash function. We go to that index. And compare. If we find the key, then we are done. If we find, we are done. We return true. or probably if it's a key value pair, then we return the corresponding value, right? Otherwise, we linearly search. We stop searching when we either find the key, or we find an empty slot, or we have traversed through the whole table. So we stop in 3 cases. When one of the 3 cases arise. Empty slot, key found, third case is traverse through the whole table. So these are the 3 cases that arise, and we stop in all these 3 cases. If we have traversed through the whole table, we return false. If we have found the key, we return true. If we found the empty slot, then we return false. So we return false in case number 1 and case number 3. Now we understand how search and insert work. Let us understand the problem with delete. How do we implement delete? Say I have these operations. I insert 50, 51, then 15, then search 15, then delete 51, then search 15. So I've already done these operations. I've inserted 50, inserted 51. When I was inserting 15, I saw a collision and inserted 51 here. Now there's an operation delete 51. So to delete, we again search for 51, and if we find it, we make the slot empty. But simply making the slot empty would be a problem. That's what we are going to discuss here. So if I delete 51, what will happen? I'll find this key and I'll make this. If I make this slot empty, what will happen? Let's see the problem with making the slot empty. So we are going to talk about problem with simply making the slot empty when we delete. So I mark this slot as empty when I encountered this delete 51 operation. Now what will happen when you search for 15? You will compute this key, right? And you will find this index value as 1. So you computed this hash function, you found the value 1, and you started searching from this slot. This does not match with 15, it's not 15, so you will come to the next slot. And now you encountered an empty slot. So when you encountered an empty slot, you say that 15 is not present. However, 15 is there in your hash table. So what do you do in your delete operation so that your search works? If you simply mark your slot as empty, then your search will fail, right? It will return false even if the key is present. So the idea is we mark these slots as deleted, right? Not empty. So this is a deleted slot. And we say, do not stop the search when you see a deleted slot. Stop the search only when you see an empty slot. So when you delete something, you mark it as deleted, and your search does not stop when it sees a deleted slot. Your insert, however, can insert in a deleted slot. So what will happen now if you search 15? You will come here, 50 does not match, then you will come here, you will see a deleted slot, and you will not stop search because it is a deleted, it's not an empty slot. You will come to 15 and you found the key. Suppose you were searching for key 64. You will begin from here, not matching. You will come here, not matching. You will come here, not matching. Now you find an empty slot. So you find an empty slot, you say 64 is not present. So in deletion, we do not mark the slot empty, we mark it as deleted. Now we understand search, insert and delete in open addressing. Let us talk about this problem called clustering with open addressing with linear probing. So what happens here is, you must have analyzed yourself, realized yourself, if there is a clash or collision in a key, you linearly search and find a position and you insert at the next position. what are you actually doing? You are forming clusters. So if one collision happens, you have a cluster of size 2. Then if any of these two keys, if any of these two indexes are going to have a new key to be inserted, then there will be a cluster of size 3. Alright, so this cluster will keep on growing. If you have 3 indexes which are occupied, 3 contiguous indexes which are occupied, if you insert a key which maps to any of these 3 indexes, you will form a cluster of size 4. Right? So clusters are formed, and these clusters keep growing a new size. Suppose there are k indexes which have formed a cluster. Now if there is a key which maps to any of these k indexes, a cluster size will become k plus 1. It will become k plus 1. If you have a key which maps to any of those indexes. That's the problem with linear probing. Due to these clusters, all your operations become costly. Search, insert, delete. Because in all the operations, we need to first search, and we stop search either when we find the key or we find an empty slot. So you will find empty slot after those many slots which are there in the cluster in the worst case. And worst case happens when you are searching for something which maps to this key and it is not there. Right? So you will have to traverse through whole cluster. So these clusters, they impact performance of open addressing. Let us now talk about how to handle this problem. So we saw a problem of clustering with linear probing. Let us now talk about how do we handle this problem. If you look at linear probing, this is something like this hash of a key when you are at ith probe can be written as your hash function plus I ampersand 7. Right. Your hash function is, say, h of key is key mod 7. This is what your linear probing is, right? So if I am at ith probing, for example, when you want to insert in a slot and you fail to insert because that slot is occupied, you begin with I equal to 1. You search your probing with I equal to 1. So when I is 1, your function is whatever this returns, go to the next slot, right? If I is 2, then go to the next to next slot. So if next slot is occupied, then you will go to the next to next slot. So that's how linear probing works. That's what we did in the previous examples. In the ith probe, we were calculating this overall hash function, which can be written as this, right? H of key plus I, and h of key is the hash function that we wrote, key ampersand 7. So this is what we were doing in the linear probing. The problem here was there were clusters formed. What do we do in quadratic probing? In quadratic probing, in place of I, we use I square, right? So that these clusters do not form together, right? If there is a slot, you just go to the next slot and next to next slot. Rather than going to the next slot, you go to I squared slot, right? So if first time collision happens, then you go to the next slot. If one more collision happens, then you go to the fourth slot, right? So first time you went to 1 square, next slot, then you go to the 2 square, fourth slot, which is, if it is also occupied, then you go to 3 square slot, which is 9th slot. And this is how you do the search. The problem with quadratic probing is still there. The problem of clustering is still there. In linear probing, we were having primary clusters. In quadratic probing, we have secondary clusters. Because your probe sequences, they are fixed. Every time you see a collision, you will follow the same probe sequence. You will go to 1th slot, then 4th slot, then 9th slot, and the next key will also follow the same probe sequence. So there are secondary clusters formed in the quadratic probing. Secondary clusters. but it is better than primary clustering. But quadratic probing has one more disadvantage compared to linear probing. The disadvantage with quadratic probing is it might happen that it does not find an empty slot even if there are empty slots, because there we were linearly searching, now we are using some other probe sequence. And there is a mathematically proven fact: if your load factor is less than 0.5 and if your m is a prime number, then only it will guarantee you that it will find a free slot. So you should have double the table size if you are using quadratic probing. Load factor half means, less than half means, the number of slots should be, load factor is what? Number of keys that you have inserted divided by number of slots in your hash table. So if this value is less than 0.5 means number of slots or your hash table size is more than double the number of keys that you have inserted. So if load factor is less than 0.5 and if m is a prime, if these two things happen together, then quadratic probing works. It finds you an empty slot. Otherwise, it is not guaranteed. So quadratic probing is guaranteed to work when load factor is less than 0.5 and your hash table size is a prime number. So if these two conditions are satisfied, then your quadratic probing works. And how does this quadratic probing work? Instead of linearly searching for the next slot, it goes to I squareth location for ith probe. Let us now talk about double hashing. So we saw quadratic probing and we saw a problem in quadratic probing. The secondary clustering was a problem. This was a problem. So an alternate idea is double hashing.